That's a misprint. Today's the 12th. All right. All right, let's go ahead and get started. We've got the orifice lab due today in lab, your reports for that, and we're going to be conducting the jet impact experiment, which is actually a real crowd pleaser. It's pretty exciting, the jet impact stuff, so I'm looking forward to that. We'll have Group B at 2 o'clock, Group A at 3 o'clock. The homework assignment you've got right now, homework 6A, will be due on Thursday, and then the follow-up to that, Part B, will be due the following Tuesday. And that also happens to be when we're having our exam, a week from today, a little more than a week from today, because we're going to do the exam at 2 o'clock during the lab time, and we'll do a software exercise during the class period time. So in class on Thursday, I'll remind you again that we'll be doing the water gems on next Tuesday during class period, so that if you want to install that on your computer, you can go ahead and do that. I'll download the installation media on the files you need onto a disk. If you're not able to connect to Bentley to download it directly, you can just borrow the disk and pass it around among yourselves. Otherwise, we have all the tablet computers, so you don't have to have it on your own personal laptop.
Who would be our administrator? I can't remember my login information.
Yeah, they say that you have a local administrator here at Marshall, but it's just Bentley has all that information. None of us, myself, Hussein, none of the other professors have anything to do with that. I mean, they send us a bill each year, but that's the extent of our involvement as administering Bentley. So if Bentley can't help you, then I don't think we're going to be able to. What's that?
I sent an email last time I had any problem, and they managed to fix it.
They fixed it, Bentley did? Okay, that's good to know that they're not just completely ignoring students, because it seems like they could get overwhelmed with student questions, but I'm glad to hear that they're being responsive about it. But I'll burn the files you'll need to a CD-ROM and make it available for you, just in case. So any schedule questions you want to ask?
The exam 2, it's been so long since exam 1. Where does it start?
Exam 2 will be chapters 4 through 6. So chapter 4 was when we started talking about fluid flowing. So chapter 4 includes convective acceleration, local acceleration, flow visualization. Chapter 4 also includes Bernoulli's and Euler's equation, rotational flow. There's a lot in Chapter 4. Chapter 5 was continuity equation, and now here in Chapter 6 we're doing momentum. So it'll be those 3 chapters. I don't know for certain yet. I would anticipate it'll be similar in format to the first exam, but I don't want to commit myself necessarily. Other questions? All right. So we're going to continue our discussion of momentum today, fluid momentum, and excuse me. This example is similar to the jet boot case. Remember that to introduce the topic of fluid momentum, we considered a wing-suited daredevil who jumped off of a hot air balloon and managed level flight by using those jet boots, those very, very dangerous jet boots with kerosene jet fuel tucked into his wingsuit, and it's just a miracle he didn't burst into flames. This example is a lot more mundane and also a lot safer. It's just, what if you had a balloon and tied it to a straw that was connected to a string, and so the gases exiting the balloon are going to provide the thrust by which the balloon could move to the right along the stream. What we know is the pressure inside of the balloon, and it's a little bit strange way of expressing pressure, but it's provided here in terms of head. They're saying that the pressure inside of the balloon is equal to 0.2032 meters of water. And so they're saying that the pressure inside the balloon is equivalent to what the pressure would be at a depth of 0.2032 meters. And so actually that's a lot more straightforward than it initially seems. They're saying that inside of the balloon, the pressure is 0.2032 meters times 9810 newtons per meter cubed. Now on the pressure gauge that you used for the energy loss lab, the Hazen-Williams lab, that's one of the pressure measurements that you could have had that device display. It could express the pressure difference in terms of the depth of water in the same way that we're seeing here. That works out to a pressure of 1993 newtons per meter squared, 1993 pascals. The nozzle diameter of that balloon is 1 centimeter. We're going to need to know the cross-sectional area of that nozzle so that we can find out what is the exit velocity. And so from using that diameter of the nozzle being 1 centimeter, 0.01 meters is the diameter, and the area, pi d squared divided by 4. The area is 7.854 times 10 to the minus 5 meters squared. The other bit of preliminary information we're given is the density of the air is 1.2 kilograms per cubic meter. So what we're going to do now is use Bernoulli's equation to tell us the relationship between the pressure inside the balloon and the velocity of the gas. Okay, so Bernoulli's equation will be useful here because if we remind ourselves the terms of the Bernoulli's equation is P1 plus gamma Z1 plus the density of the fluid times V1 squared divided by 2 is equal to the pressure at 2 plus gamma Z2 plus the density V2 squared divided by 2. That's Bernoulli's equation in terms of pressure rather than in terms of head. So let's consider what we're talking about. We've got a balloon here, and what is 1 and what is 2? Well, what we're going to say is let's have 1 be in the middle of the balloon, and let's have location 2 be just outside of the balloon's opening. Okay, we've got a little opening that those gases are flowing out of. Inside the balloon, the pressure is 1993 pascals. Outside the balloon, the pressure is 0. It's just atmospheric pressure. So this pressure that we had of 1993, that's where they were saying what is the pressure inside the balloon over and above the pressure of the surrounding atmosphere. And so we're going to say P2 is 0 and P1 is 1993 pascals. We're going to be canceling out P2, setting it equal to 0. Now, you can see that 1 and 2 are on the same plane. They don't have any vertical elevation difference. And for that reason, we're going to cancel out the Z2 and the Z1 terms. Now, at 1, there isn't any fluid velocity. There is air that's moving towards the outlet, moving towards the opening of that balloon. But at 1, it's so slow that it can be neglected. So we're going to say that V1 is 0. That essentially, think about how a balloon works. The balloon sort of collapses in on itself as it's contracting, and so the air at 1 is motionless, where we've measured the pressure. So all we know, what we know so far, is that the pressure at 1 is going to be density V2 squared divided by 2. That simplifies nicely. Any questions so far on how Bernoulli's equation is going to be used to tell us the velocity? All right.
Given the P1,
Uh-huh.
the way that's worked,
Exactly. Yep. If it gives you depth or a head, you can calculate the pressure directly. What they essentially said in that statement is P divided by gamma is 0.2032 meters. They called it a pressure, but it was really the pressure head inside the balloon is 0.2032 meters. And that's sort of a common abbreviation. It's not necessarily a mistake. It's just a convention that sometimes pressure and pressure head are interchanged in a little bit of a sloppy way like it was here. But like you point out, all you need to do is multiply it by the unit weight and you're back on track.
Do you see that with any other kind of fluid or just water typically?
Well, water is the most common fluid that we'll work with, but they could say it with any fluid. It wouldn't necessarily have to be water. All right, so we rearrange this to solve for velocity, and we get that the velocity is equal to the square root of 2 times the pressure divided by the density. Okay, so the square root of 2 times 1993 newtons per meter squared divided by the density, which is 1.2 kilograms per cubic meter. Now, how are we going to get meters per second, which is our units for velocity, out of the units that are displayed so far? That's right. Break the newtons up into its components, which is a kilogram meter per second squared. So that's going to be kilogram meter per second squared. Okay, so here we had meters cubed in a denominator. Here we're going to have meters to the 1 power in the denominator. So it's going to put that up into the numerator. So we'll have meters squared per second squared as the units, and then take the square root of it. Ultimately, we can find that the velocity is 57.6 meters per second. So that's the velocity of the air as it exits the balloon. Now, what about the force that it's able to, that's required to hold the system steady? So you can see that they've already indicated with the arrow there that the force is going to be to the left. If we apply the momentum equation to that, let's find out what the magnitude of the force is. What's missing for us to calculate the magnitude of the force? What don't we know yet? Okay, that's an interesting idea. If we knew the volume of the balloon, then we could maybe find out how long it can apply the force. But we don't actually have to know the volume of the balloon just to find like the force at this instant in time. We're just talking about like right at this particular instant when the pressure is 0.2032. Presumably the pressure in the balloon is probably going to be decreasing as it continues to discharge. What we don't know yet, though, is the mass flow rate. Because remember that if we have a control volume around this balloon, so here's our balloon, here's our control volume, what we're going to be doing is keeping track of the flow of momentum out of that control volume. And so we want to know what is the mass flow rate times the velocity. There isn't any jet coming in. There's only out here. And so we need to find out what is the velocity out. We just did that. We found that the velocity out is negative 57.6 meters per second. The negative because it's to the left. Remember that it's critically important when we're doing these momentum problems to get the direction convention honored correctly. To the left is negative, down is negative. And it's also important to keep track of its out minus in, as shown in the formula there. We're keeping track of the mass flow out minus the mass flow in. All right, so there's nothing going into our control volume. From the drawing you can tell that, but there is something coming out of the control volume. And so the generalized formula of the mass flow equation here, giving us a force required to hold the system steady, will add up through the control surfaces all the mass flow rate out, the velocity out in x minus all of the flow through the control surfaces, the mass flow rate in, and the velocity in x. Now there's nothing going in, so this whole term cancels out. And there's only one stream. So where it's saying the sum of the streams here going through the control surface, there's only one stream. We'll have some problems where there's multiple jets entering the control volume, but here it's just a single jet. And we're going to apply the force at just a single location, so it's not going to be a series of forces that we have to sum together. So I'm going to say the force required to hold the system steady in the x direction is the mass flow rate out times the velocity out in x. The mass flow rate is density times the volumetric flow rate, or density times the velocity times the area. Now, there's a mistake that would be easy to make. There's a mistake sort of lurking there trying to lull you into making it. What if you said density, velocity, area. So this is the mass flow rate, right? And here we've got velocity out in x. What's the mistake of combining those two velocities together? What's like the potential error if you combined it all together and just made it look like this? Density, area, v squared. What would be the problem with that?
It's just the horizontal velocity component.
Okay, all right. Let's say that, that we make sure it's only the horizontal aspect of it. So that is one mistake. He's pointing out that geez Louise, today's not the day to bend over. I am sore. So if there was a stream that was going in x and y, then one mistake you could make is not just finding the horizontal component of it. But let's say that we are just finding the horizontal component of it.
Q value is not to be kilograms per
The Q will be in cubic meters per second. So it's not actually the units issue. That's not the error. You could forget one of the velocities. Well, we've got them both there. When we're saying v squared, we've accounted for both of them. Said the problem is that mass flow rate is a scalar and velocity is a vector. And so mass flow rate doesn't have a direction. It's just only got a magnitude, whereas the velocity will have a direction. So this is, don't do that. I shouldn't even write it on the board, or you'll be tempted to maybe think it's the right thing. Okay, mass flow rate is the density, velocity, and the area. Okay, this v, it doesn't matter if you put a negative sign or a positive sign in it. Actually, you shouldn't put a negative sign because mass flow rate is just a scalar. It only has magnitude. But the second velocity, this one has to have a sign associated with it. And so the mistake is this velocity is to the left, right? So that's going to be a negative velocity. So this needs to have that negative sign in it. But if you did velocity squared and the velocity was negative, then you'd lose that negative sign that needs to be there to indicate that the force is to the left. So in other words, don't just square the velocities, because then your equation won't be able to tell you what direction the force is in. Let me illustrate that with specific numbers. Okay, here we've got a density of 1.2 kilograms per cubic meter. Our velocity is 57.6 meters per second, and the cross-sectional area of 7.854 times 10 to the minus fifth meters squared. And then this velocity is going to be negative 57.6 meters per second. So this velocity, I didn't put the negative sign in because mass flow rate doesn't have direction. It's just a quantity that only has magnitude. But here, this velocity, I put in the negative sign because that is the one that is going to tell us whether the force is to the left or to the right. We calculate here, when we do the calculations, we find that the force is negative 0.31 newtons. So the force should be to the left to hold the system steady. But if we had done that thing of just squaring the velocities, then that wouldn't have told us that it's to the left. So the thing to keep in mind is that mass flow rate is a scalar, velocity is a vector, meaning that it has both magnitude and direction. Any questions about that? Yeah.
If it was at an angle,
Yeah.
would that velocity and mass flow rate be the
Okay.
magnitude? Or
Good
just
question.
the horizontal?
I think I get what your question is. All right. Let me draw this scenario a little bit differently just to illustrate the point that he raises, and it's a good one. All right. Let's say that the balloon is like this, and then here's its jet. So it's got some mass flow rate. Its mass flow rate is going to be the density, the area, and the velocity. And so we said that the density was 1.2 kilograms per cubic meter. The area is 7.854 times 10 to the minus fifth meters squared, and the velocity is 57.6 meters per second. So when we put it in to find what are the forces in the x direction required to hold the system steady, it's going to be the mass flow rate out times the velocity out in x. You'll notice that it's not saying the mass flow rate in x. So it's the absolute quantity of the mass flow rate multiplied by the velocity component that's in the x direction. So you'd use the full velocity of 57.6 to find the mass flow rate, but then so if anybody do the calculations real quick here and tell us what the mass flow rate is when we do 1.2 times the area times the velocity. And that's going to be kilograms per second. Thank you. 5.4 times 10 to the minus third kilograms per second. That's the mass flow rate, regardless of whether it is at a full in the x-plane or if it's at a 45-degree angle or if it's in y. The mass flow rate is just the mass flow rate. But now it's only in the x direction, the velocity component, that we're interested in. So if we wanted to find what force is required to hold the system steady in x, we would say it's going to be that 5.4 times 10 to the minus third kilograms per second. And then, since it looks like this is a 45-degree angle, then we'd say the sine of 45, so it's 0.707 times the velocity in 0.707 times the 57.6 meters per second, with the negative sign there to indicate that it's to the left. So the force required is going to be less than when it was strictly in the x direction. We're not going to have to push as hard in the x direction. We're going to have to push down, of course, to hold the balloon steady. But your question was essentially how to handle the velocity here when it's at an angle, right? You use the full velocity to calculate the mass flow rate. Other questions? Yeah. Yeah, as the balloon empties, it's not going to push as hard, is it? And so when it asks for the force, it wants to know what's the force when the pressure is equal to the value that they've described. The other thing to point out is look that they've already, in the drawing, indicated the magnitude of the force. And so you can accidentally shoot yourself in the foot if you have like a quiz or an exam or a homework problem and you're trying to find out what force is required to hold the system steady. Let's say you've got a jet of water and you're deflecting it upwards. So you're using like a ramp to deflect it upwards. So this jet of water gets deflected because of that ramp. So if the question is, what is the force required to hold the system steady? What if you said this? So what would be the potential problem of drawing it like that and then listing the magnitude of the force? When you've got the arrow shown to the left, you're already saying the direction of it, but then when you say the negative, that's like saying the opposite of the direction shown. It's a double negative. And so we know, just from looking at it, that we have to push that direction, right? So if you've got the direction indicated in the drawing, then you should say force equals 10 kilonewtons, direction as shown. Or the other way to do it would be, you'd say, here's F, and F would be negative 10 kilonewtons. So that you're not doing the double negative thing. So the direction should be to the left, and you're either going to indicate that with a negative sign on the magnitude or on the drawing itself. The main thing that I'm looking for when I grade a quiz or an exam is I want you to demonstrate that you definitely knew what direction that force had to be applied in. And there can be ambiguities sometimes that I'm not certain necessarily you knew what the direction was. And so there's no such thing as too much information when you're telling me what the direction is. So you can either draw it on the picture and say direction as shown, or just make it abundantly clear. Was there a question? Yeah, Evan?
In the example, should we have 0.31 positive
0.31. I'm not following you. Oh, okay. So 0.31. So if we have, this is back to the original example where the nozzle was exiting here. All right, so the force. If we have that force shown to the left, then yes, we should say force is 0.31 newtons. Or another way to say it is force required is 0.31 newtons to the left as shown. So that was one of the situations where if we were already showing it to the left and I had the negative sign, then that could lead to confusion of is it to the left or is it to the right. So we don't want there to be any ambiguity. Thanks for raising that point. All right. We've been staring at this balloon long enough. There's more interesting examples out there. All right. These are the three main categories of problem types we're going to be working on. They're going to have fluid jets, we're going to have nozzles, and we'll have vanes. And all three of these problem types use the momentum equation that's shown there. And remember, of course, this is just showing the form of the momentum equation in the x direction. There's also an equation in the y direction where anytime you see x, you just substitute y. So f sub y velocity out in y, velocity in y. But there are other things we're going to combine with these problems in addition to the momentum equation. Like, for example, here in this balloon problem, we did Bernoulli's plus the momentum equation. I mean, what makes these a little bit more challenging is that there's going to be combinations of ideas together. So there may be, Bernoulli's, I guess, will be the most common one that we'll have to apply a couple of times, particularly when it comes to nozzles. The jets and the vanes are pretty straightforward. The nozzles can be a little bit tricky, though. Well, let's try out this example here. And I'd like you to do this one either with somebody sitting next to you or by yourself. Try and figure out for this tank of water, there's a 15 meter per second jet entering the tank. Now, the tank itself has 5 kilograms of mass, and it has 20 liters of water. So find what force is acting on the stop block, and then also what force is acting on the bottom of the tank. What the surface that it's on is pushing up to support the tank, and what are both of those forces? It's not moving, so friction won't apply. Start off by drawing a little diagram of the tank. It can help us to understand that there is a weight force having to do with the tank and the amount of water that's there, a force that's being applied by the stop block to the tank, and then there's going to be a force of the surface pushing up on the tank to support it. We're going to need to know the mass flow rate, and maybe it's a little bit picky, but at 15 degrees Celsius, the density of water is 999 kilograms per cubic meter instead of 1,000. If you wrote 1,000, it's probably close enough that there's no sense changing it, but that is the density at that particular temperature. The area we're talking about is the area of the jet diameter. And so we're finding the mass flow rate by finding the volumetric flow rate, which is the area times the velocity of the jet, then multiplying that by the density. And so we get a mass flow rate of 10.6 kilograms per second. There's nothing flowing out in the x direction, or the y direction for that matter, but right now we're just looking at the x direction. So there's no mass flow out or velocity out, so that term is equal to 0, minus the mass flow rate in times the velocity in. So the force required to hold the system steady in x is going to be the negative of the mass flow rate, which is 10.6 kilograms per second, multiplied by the velocity. Now, the velocity component that's in the x direction will be the cosine of 70, multiplied by negative 15 meters per second. And it's important for us to preserve that negative sign there so that it tells us the force required correct direction. That works out to be 54.3 newtons. Okay, so the arrow is showing to the right, and we've got a positive sign there for the number, so that doesn't override the direction that's indicated by the arrow itself. So the force required to hold the system steady in X is going to be 54.3 newtons to the right. So I'll say, in other words, i.e., force required to hold the system steady is to the right. And now this says the force acting on the stop block. It's in italics there, just as a reminder that sometimes it's asking for the equal and opposite. This, the momentum equation finds the force required to hold the system steady. But now this is the force of the jet acting on the block rather than the force of the block acting on the jet. And so it would be force is negative 54.3 newtons acting on the stop block. Okay. So indicating the force is going to be to the left. That's the water acting on the stop block is to the left. And so any questions about finding the force in the x direction so far? The y direction is going to be largely the same approach. It's just we're going to use the sine of 70 instead of the cosine of 70 because we're going to want to know the component of the velocity that's in the vertical direction. So now the y direction, we start off by having the equation. The sum of the forces in the y direction are going to be the sum of the flows through the control surface out in y minus the flow through the control surfaces, the mass flow rate in, velocity in y. Now the forces here, there's more than just the force required to hold the system steady because there's also the weight of the tank. And so the forces that are going to be in play here are going to be the normal force is up minus the weight is going to be down. We're ultimately going to be finding the normal force. How much does the horizontal surface that this tank is resting on push upward to support the tank? Okay, so we've got the normal force acting up, the weight is acting down, and that's going to be, there isn't any mass flow rate out once again, so it's 0 minus the mass flow rate in and the velocity in y. The weight, by the way, W, is going to be both the weight of the tank and the weight of the water. We'll account for both of them. So the tank weight is 5 kilograms times g, 9.81 meters per second squared. And then the weight of the water, we know that the volume of water inside the tank is 20 liters. That's pretty close to 20 kilograms, but to be precise, we'll keep track of what's the density of the water at this particular temperature, 999 kilograms per cubic meter. Okay, so the sum of the weights is 245.1 newtons. Now, back over here, we've got the normal force is going to be W minus the mass flow rate in and the velocity in y. So that is the 245.1 newtons minus the mass flow rate in. We previously already found the mass flow rate was 10.6 kilograms per second. And then the velocity in, I don't something. Let's see. Oh, you know what? You're right. What I should have done is used gamma. Thanks for catching that. So it's 9,800 newtons per meter cubed at 20 degrees Celsius. Thank you. So volume times gamma will give me the weight rather than the mass. So I had just found how many kilograms of water there was, and I need to convert it from kilograms into the number of units by either multiplying what I had by G, or instead of using the density here, I should have used the unit weight. All right. So I've got the mass flow rate, and I'll need to find the velocity component in the y direction. So that velocity component in the y direction is going to be the sine of 70, and then the velocity is down, and so it is negative 15 meters per second. So I've got the negative sign here that's just on account of this being the inflow term, which has that negative sign built into the formula. And then since it's downward, I've got that negative sign, and the two are going to cancel each other out, which means the momentum is going to have a positive effect on how much force has to be pushing up on the tank. So this is like a tank sitting on a table. The table has to push up more than it would if that momentum flow wasn't there. Just think about if it was just a stationary tank of water, then it would have to push up 245 newtons. But this momentum part of it accounts for an additional 149.3 newtons. So that's how much extra the surface is pushing up on the bottom of the tank because of the momentum flows here. And so the total normal force upward will be 394.4 newtons when you account for both the weight of the tank, the weight of the water, and then also the momentum forces. And so it asks the force acting on the bottom of the tank. And we don't have to sort of switch sides like we did on the horizontal forces, because we've already taken into account the normal forces acting upwards, and that's what it's asking for. Because that's the force required to hold the system steady. Let's say that the system is the tank. So here's our tank, and we're drawing our system boundaries to include just the tank. And now, when it was asking the force acting on the stop block, here's the stop block, it was acting, that was outside of the system. So it was sort of like the, not necessarily the force holding the system steady, but the force of the system on an external part. But on the second one, the vertical forces, the force acting on the bottom of the tank, that's another way of saying the force is required to hold the system steady in the vertical direction. So we don't have to flip the sign of it, because the force is upward, which is the positive y direction, to hold the tank steady. So I guess it goes back to how we interpret the momentum equation. Remember that this equation, the way in plain English that we interpret it is the force required to hold the system steady. So this one is not the same thing. The force acting on the stop block is not the force holding the system steady. It's the opposite of that. But the force acting on the bottom of the tank, that is the force that's holding the system steady. Other questions? All right. We've got time for this one last example, and this is the trickiest of all. Once you figure out this, then these momentum problems just sort of fall into line pretty quickly. Here we've got a nozzle that is changing the diameter of the flow. And what happens when flow diameter changes? Okay, the velocity changes and the pressure changes because Bernoulli's equation. So that's right. As the diameter contracts in this case, there's a convective acceleration, meaning that the flow velocity is changing with respect to position. Here at 1, the velocity is moving slowly, and as a result, it has relatively higher pressure. And then as it accelerates, because the cross-sectional flow area decreases, then the velocity goes up, the pressure has to decrease. Excuse me. Now, this pipe continues that direction. It's not like just all of a sudden mass is created and it's entering some nozzle. It's just not pictured. And so what we're doing is we're taking a continual pipe that continues onward in the left, and we're cutting it with an imaginary line. That control surface is what we're using to cut the pipe, and so that we have what's essentially an external force acting on that cut pipe. Let me show you what I mean. We had some pipe, and it goes to a nozzle, and water is coming out of a jet. I'm going to just draw a control surface. And now the water that is on the left side of that control surface is acting as though it's an external force. And so when we do the momentum equation, when we say the sum of the forces in x is the mass flow rate out, the velocity out in x, minus the mass flow rate in the velocity in x, there's going to be these forces. The water pushing on the control surface is going to act as though it is one of these forces on the left-hand side that we're talking about. So the interpretation is going to be that this nozzle has like a flange here that we're putting a force on. We're applying a force to hold it steady. And think about a hose. When you're holding onto a hose, it may push back a little bit. You'll see firefighters maybe leaning into it as they hold onto the hose because it's going to be flying all over the place. So there's a flange here that in the x direction, we're applying some force in x. In addition to that, because we've cut a pipe that's pressurized, not physically cut it, but when we do the calculations, since our control surface has pressure on the other side of it, we have to say there's the force in x plus the pressure times the area is equal to the mass flow rate out, velocity out in x, minus the mass flow rate in, the velocity in x. So pressure times area here becomes an external force. You know, this pipe is pressurized, and there is some cross-sectional area that force is acting on. And so it's effectively an external force to the control surface. So we want to know what force is required to hold the nozzle in place. And we have some preliminary information here. We know the diameters, and from that we'll be able to find the cross-sectional areas and so on. So we'll do the preliminary stuff. We've got a flow rate of 0.3 cubic meters per second. Q is 0.3 cubic meters per second. And D1 of 0.30 meters, that's going to lead to a cross-sectional area, pi d1 squared divided by 4. The cross-sectional area at 1 is 0.07069 square meters. And we know that D2 is 0.10 meters. and that leads to the area at 2. The same way, we can calculate the cross-sectional area at 2. It seems like I didn't calculate it separately. Somebody with a calculator find the cross-sectional area at 2. 10 to the negative 3. Thank you very much. All right. We can find the velocities at 1 and 2. The velocity at 1 will be the flow rate divided by A1. Okay, so 0.3 cubic meters per second divided by the area at 1. And we find the velocity at 1 is 4.24 meters per second. And we can find the velocity at 2 in the same way. And the velocity at 2 is 38.2 meters per second. So just based on that, what would you guess, what direction are we going to have to push in? That the mass flow rate will be the same, but the velocity out is greater than the velocity in. So what direction? Are we going to have to push to the right, or are we going to have to push to the left to hold the system steady? What do you think? Think about that. The velocity out is big. The velocity in is small. And so if we're only thinking in terms of the change in velocity, we're going to have to push to the right. But keep in mind, we've got this pressurized pipe, so the pressure times area may throw a curveball in here. And in fact, it will. It will. Let's use Bernoulli's equation, first of all, to find out what's the magnitude of the pressure at 1. Bernoulli's equation will tell us that. Bernoulli's. We have that the pressure at 1 plus gamma Z1 plus the density V1 squared divided by 2 is equal to P2 plus gamma Z2 plus the density velocity 2 squared divided by 2. Okay, so the jet of water that comes out at 2 doesn't have any pressure. It's at atmospheric pressure. As soon as the jet is surrounded by air, like it is here, then that means that the pressure inside that jet is 0. And so pressure 2 is equal to 0. Z1 is equal to Z2 since it's a horizontal element. So that allows me to calculate the to cancel out the elevation term and to cancel out the P2 term. And so the pressure at 1 is going to be a function of the difference in pressures. It'll be the density divided by 2, V2 squared minus V1 squared. Yeah, because it's surrounded by air. That jet doesn't have any pressure. The water can't be pressurized when it's not surrounded by the nozzle anymore. It instantly loses its pressure when it comes out of the nozzle. So we'll find out what is pressure at 1 by using the difference in velocities. That works out to be 720 kilopascals, 720,000 newtons per meter squared from the difference in velocities multiplied by the density divided by 2. Okay. So that's Bernoulli's equation. It tells us how big the pressure is at 1. In other words, there would have to be that much pressure at 1 based on the difference in velocities that there is between 1 and 2. So now in the momentum part of the problem, we can say that the force required to hold the system steady, the sum of the forces, is equal to the mass flow rate out, velocity out in x, minus the mass flow rate in, the velocity in x. And that's where the pressure starts to act as an external force. P1A1 plus the force that's applied at the flange is equal to the mass flow rate out, and we're going to get the mass flow rate out by the density times the volumetric flow rate, and that then will be multiplied by the velocity out, which is V2 minus V1. Yes? Oh, okay, good question. That flange goes all the way around the pipe. It's a circular pipe, and so it's sort of like a ring or a donut. So we're just assuming that the force that's holding the that flange is all over there. So, and even if there were two of them, what we'd just be calculating is like the net force. And so, you know, if you saw in the picture that there were two of them, then maybe you'd divide the total force by 2 and say, you know, that much each or something like that. But in this case, since it's circular, there's only one of them. I'm glad you asked that. That's something I ordinarily point out.
Oh, what did you say about the right side of the formula?
Over here?
Yeah.
Okay, the mass flow rate's the same, so mass out and mass in's the same, so we just gather them together as the density times the flow rate. And then velocity out is that jet velocity 2, and velocity in is V1. So I've just sort of consolidated the mass flow term, and then I've got V2 minus V1 remaining. So that if I want to find the force on the flange, it's going to be P1, well, it'll be the 1,000 kilograms per cubic meter, that's the density of water, times the volumetric flow rate of 0.30 cubic meters per second. The difference in velocity, 38.2 meters per second minus 4.24 meters per second. And now minus P1A1. So minus 720,000 newtons per meter squared times the cross-sectional area, 0.070686 meters squared. Okay, so this part of it is 10,188 newtons, and that part of it is 5894 newtons. Remember when I asked that question just at the beginning is, would you have to push to the right or push to the left? We're already getting used to thinking about the momentum part of it, and we would have to push to the right to overcome the momentum. This 10,000 newtons of pushing to the right is because of the change in velocity. But the fact that inside the pipe the water is pressurized, on the outside of the pipe it's not, balances that out with 50,000 newtons to the left. And so the net force that we're going to have to apply to the flange to hold the system steady is actually negative 40706 newtons. So, in other words, to the left. We have to push on the flange to the left to hold the system steady because of the difference in pressure. Now, that could change if we had a different pressure differential. It might be that the momentum forces are greater than the pressure forces, but in this case they weren't. Are there any questions about that? In the lab today, we are going to be working with a jet, similar to this, I suppose. We're going to be able to change the angle of the water that gets deflected by the jet. Just a couple of minutes, so let me do a drawing here and show you the 4 deflector plate angles we're going to be working with. All right, so there's a jet of water going straight up, and the first deflector will change it 30 degrees. The second deflector will change it 90 degrees. So here's the water jet. It goes that way. Here's one, and we're going to have another weight. And then there is a 120 degree piece. The water comes up and changes angle. And finally, one that claims to be 180 degrees, but it's not exactly 180 degrees. So we're going to be adding these little brass weights to sort of cancel out the force that the jet is applying to the deflector plates. For the 30-degree angle, we're going to have to apply a different amount of weight on the top than we will with a 180-degree angle. Which one of these 4 do you think we're going to put the heaviest weights on for the same flow rate? If you consider if we left the jet flow rate at the same setting, which one of them would we put the most weight on, and which one would we put the least weight on? 180 will need the most, that's right, because it's changing the direction most extremely. Remember that the force is the mass flow rate times the velocity out minus the velocity in. And so where velocity out and velocity in have the biggest difference is going to lead to the biggest force. Here, this deflector really isn't changing the velocity that much. It's only changing it from being 100% vertical to mostly vertical. Whereas here, you know, it's a pretty drastic thing. Basically, there is no velocity out in the vertical direction. There's only a velocity in. But then the 120 and the 180 go even further than that. Rather than removing the velocity out completely, it changes it the opposite direction. And so it's going to be an experiment where we'll do 2 different runs for each one of these deflector plates. We'll have a high flow rate run and a low flow rate run. And what we're going to do is add a certain amount of weight to it and then very carefully adjust the flow rate so that it gets into this equilibrium position. And we're going to try and find out, how does it match up? Does the predicted force that the momentum equation tells us match how much force we applied with those little brass weights that were added to the top of the device? So it's a comparison or a validation of the momentum equation, because theoretically we know, based on the flow rate that we're going to quantify, you know, we're going to quantify flow rate with the stopwatch and the dropping the plug inside of the bench. So we'll know Q, and from the flow rate, that allows us to find the mass flow of the jet. Mass flow of the jet will be the density times the flow rate. You know the diameter of the jet. The diameter is given And so that allows you to find the velocity of the jet for every single flow rate. And so you'll know everything you need to find the force. It'll be the mass flow rate out, velocity out in y, minus the mass flow rate in, mass flow rate in, velocity in y. So you'll be able to quantify the mass flow rate and the velocities directly from knowing the diameter of the jet and the flow rate. And so there will be like a theoretical force, and then there will be the actual force, because you're going to actually know with the brass weights how much force you had to apply to resist the momentum force. So that's what we're going to be up to today in lab. I'll see you at 2 o'clock and 3 o'clock. Yes, lab's due in lab.